Hello, everyone. My name is Tom Sachin. I'm a student at Princeton University, participating in the Math REU program at Tufts University this summer, specifically in the Geometric Group Theory Research Group. Today, I'm going to talk a little bit about the so-called growth of finitely generated groups, what that means, why we care about it, and some of the broader implications in algebra and geometry. I'll say now that for the remainder of this talk, whenever I refer to a group, you can assume that the group is finitely generated unless stated otherwise. So if I just say, a group G, you can assume that G has a finite generating set, which is implicit. So I'll begin by first defining what we mean when we say the growth of a group G. If you want to think about it sort of conceptually, you can imagine taking turning G into a metric space somehow, and then taking balls of radius R in G, and seeing how the volume of these balls increase as we increase R. More precisely, if we have a finitely generated group G, we can impose what's called the word metric on G, which is a very natural metric on any group, which you may have seen, where the distance between any two elements G and G prime in G with respect to the generating set S is just the length of the shortest word representing the difference between these two elements. So G times G prime inverse. So this gives us a very nice metric. You can verify for yourself that it is indeed a metric on G. And this allows us to define balls of radius R. And you can see here that our growth function, which we'll call beta, is just a map from R, and R is a natural number representing the radius. That takes it to sort of the volume of a ball of radius R and G. In other words, it tells you how many words in G have length less than or equal to R. Okay, so that's very nice. And immediately you can sort of start thinking about geometric interpretations of this. Many of these and many things in general in geometric group theory include what's called a Cayley graph, which is a graph that we can associate to any group for a sort of a nice geometric way of understanding intrinsic properties of the group. And the properties of this graph are that the vertex set of the graph is just the set of elements in G. Maybe I can draw sort of squiggly brackets around this G to make that a little more explicit. And the set of edges in our Cayley graph, this looks sort of convoluted, but the set of edges in our Cayley graph are such that any two vertices are connected if and only if we can reach one from the other by one application of the generator, of a generator, I should say. So one very basic example, which you'll see on sort of page 3 of any geometric group theory textbook, is the number line, Z. So if we want to draw a Cayley graph for Z, we start at the identity element. We apply and of course, we're looking at Z with the generator 1. You can draw Cayley graphs with different generating sets, but if we apply this generator 1 time, we reach another element, which we call 1. If we apply it twice, we reach 2. And similarly, we can apply the inverse of the generator to get -1, -2, -3, and et cetera, et cetera. And so you can already see that this is a nice way of trying to understand geometric properties of groups, which are not a priori geometric objects. Another pretty popular example is the Cayley graph of the free group on 2 generators. So here you can see the free group on 2 generators. All right, on generators A and B, and the Cayley graph looks something like this. You may notice it's a 4 regular tree drawn in the plane. And I'll say the notable thing about this Cayley graph is that it's a tree, which means that it doesn't have any cycles, and sort of a graph not having any cycles is a geometric sort of visual property. But what it tells us about the group is that there are no relators in the group. Because if we had a cycle in the group, we could start at one point and walk around it via a word in our group and return to where we started, which is another way of saying we have some word that's equivalent to the identity. So something that maybe you can prove for yourself is that the Cayley graph of any free group is a tree. Great. So if we want to understand growth just by looking at the Cayley graph, we can start at the origin and walk along all paths of length less than or equal to r, and every element that we reach on our journey will be in the ball of radius r. Okay. So now I'm just going to introduce a little bit of notation that's going to make sort of the punchline of this talk make a little bit more sense. So we have ways of comparing growth types of groups. In fact, these ways of comparing are sort of the most natural. There are ways that you've looked at comparing growth types of different, functions and things like that in the past. So if we have two groups, G and H, with respective finite generating sets S and T, we have this relationship called quasi-domination, where we say that the growth function of H quasi-dominates the growth function of G if we have these constants C1 and C2 that we can arrange in this way to make this equation true for all R, for all radii R. You can sort of think of this like one function dominating another function, except not quite, because it's sort of fuzzy up to these additive and multiplicative constants. And when we have one growth function that quasi-dominates another, we have this notation with this sort of drunk less than or equal to sign. And in fact, we also have a relation called quasi-equivalence. So if we have two growth functions, in this case, the growth function of G and the growth function of H, if they both quasi-dominate each other, then we say that their growth functions are quasi-equivalent. And you can think of this as the growth functions essentially growing at the same rate, right? So if one grows like a polynomial in degree n, then the other grows like a polynomial in degree n as well. But there might be some weird additive and multiplicative constants in there that we don't really care about at a large scale. And in fact, this is a common theme in geometric group theory in general, is that we have these sort of quasi things. We have things called quasi-isometries and quasi-domination and quasi-equivalence and everything like that. And the reason is because we're really concerned with large-scale geometry. When you sort of study the asymptotic geometric behavior of things as they approach infinity, or you squint your eyes and don't look at the little details, aka when we insert these constants, that's the things that persist through that are the types of geometric features that we're really looking for. Okay, so maybe you can convince yourself as well, this is sort of an exercise if you'd like, that quasi-equivalence is an equivalence relation on the set of growth functions of finitely generated groups. And in fact, these equivalence classes are called growth types. Great. So far, everything is very natural. We're just sort of looking at different types of groups and how quickly they grow as we look at words of longer and longer length. All right, so I'll just briefly give some examples of actually computing the growth of familiar groups. So the first example I'll give is I'll claim that the growth rate of z to the n is quasi-equivalent to a polynomial of degree n in R, where R is once again the radius. I don't quite have time to prove this to you fully, but a good way of convincing yourself that this is true is just by remembering the volume formulas that you learned in middle school or whenever for circles and spheres. And maybe you'll remember that the volume of a circle, the area of a circle, I guess, is pi r squared. The volume of a sphere, a solid sphere, is 4/3 pi r cubed, and the volume of a one ball is just 2r. So you can see that in each case, the volume of an n ball is like a polynomial of degree n in R. This goes on and on as we integrate, as we continue to integrate. And maybe you're saying, well, now you're talking about n balls, you're no longer talking about z, you're no longer talking about z to the n. And the reason for this is because a ball in z to the n is what's called quasi-isometric to a ball in Euclidean space, which I'll talk about in just a minute, but z to the n is quasi-isometric to r to the n, which for now, let's just say means that if you really squint your eyes and zoom out, they sort of look the same. They're not quite isometric, meaning distances aren't preserved under a map from z to the n to r to the n, but it's close up to some additive and multiplicative constants. If you'd like to consider z squared, the Cayley graph of that looks like the integer lattice, which sort of embeds nicely into r squared, which is just the plane. We can draw the integer lattice in the plane nicely, and maybe you can convince yourself that distances between points in the integer lattice are close enough to distances between their images under this inclusion map. Another example of computing the growth of a familiar group is computing the growth of Fn, the free group on n generators. And I claim this time without proof that it is quasi-equivalent to e to the r, where once again r is the radius. And this will tell you that F2 grows at the same rate as F61. Okay. A natural question is, do there exist groups of intermediate growth, i.e. groups that grow faster than polynomials, yet slower than exponentials? Maybe it seems like a sort of basic question at first, but in fact, this was an open problem for many years, posed in 1968 by John Milner, and finally answered by Ukrainian mathematician Grigorchuk in 1980. He answered, yes, there are groups of intermediate growth. In fact, he constructed them, and you can see his construction for yourself if you wish. All right. So I talked a lot about quasi-isometries, but I didn't say what it is. So now I'll say what they are. A quasi-isometry is a map from a metric space G to a metric space H. In this case, we're still thinking of our groups G and H as metric spaces with the word metric. And I have these two sort of ugly conditions, but you don't have to stare at them. All that they're saying is that distances in G between any 2 points G and G prime are close to distances of their images under phi, up to these additive and multiplicative constants arranged like this. Okay, and we also have a condition called quasi-surjectivity, or maybe you've heard coarse surjectivity in the past, where for any point in our image H, there's a point of the image of the map phi that is nearby. And by nearby, it's within some uniform constant I called C2. So there's no big gaping sort of unbounded areas in H where there's no sign of the image of phi. So you can think of these groups as being sort of nearly isometric, but there's this fuzziness, there are these additive constants. And like I said earlier, a nice easy example of this, which you can prove without too much difficulty, is, let's just say Z2 is quasi-isometric to R2. All right, great. Now I claim, once again without proof, although this time there's a sketch of the proof, so you can sort of follow that and do it yourself at home if you'd like, that growth type is a quasi-isometry invariant. So the notion of growth and the notion of quasi-isometry are sort of deeply intertwined, because any two groups that are quasi-isometric grow at the same rate. Meaning, for example, a very basic consequence of this is that z to the m is quasi-isometric to z to the n if and only if m equal n. So no two powers of z are quasi-isometric to each other. if m does not equal n, because they grow at different rates, because one grows like, this one grows like x to the m, and this one grows like x to the n. No bueno. So already we're learning a lot about quasi-isometries just from growth considerations. And like I said, here's a sketch of the proof. I don't have time to go through it right now, but if you want to pause the video at some later point and do it yourself as an exercise, feel free. All right, so now for the punchline, sort of why we care, why we're looking at these things at all. One is something called Gromov's theorem, in which we'll learn something very deeply algebraic about a group just by looking at its growth. Growth sort of seems like a sort of a geometric notion, especially when we consider growth in the context of a Cayley graph. And yet we can learn something about the nilpotence of groups. Great. And the other thing we'll talk about is similar to what I was saying earlier about how the growth rate of z to the n looks like the growth rate of r to the n, because we have these balls in r which look like balls in z. And what I'll be talking about is the way that the growth of the volume of a Riemannian manifold corresponds to the growth of its fundamental group, which is a very deep idea in geometric group theory that we can understand using growth. All right, so since we're running a bit short on time, I'm just going to state these two theorems and comment on them a bit. I won't provide any proof, but if you have any questions about this presentation, it would be awesome if they were asking about these theorems, because this is sort of the punchline of this entire talk. This is why growth is interesting and important and applicable to other stuff. I guess beyond aesthetically, it's nice. So the first of these theorems is Gromov's theorem, which is a very fundamental, significant theorem in geometric group theory, first stated and proved in 1981. And very simply, the statement is finitely generated groups have polynomial growth if and only if they are virtually nilpotent. So just some terminology. We say a group G is virtually another group H if G contains a finite index subgroup isomorphic to H. So such a group, in this case, has a finite index subgroup isomorphic to a nilpotent group. Okay, and nilpotent, if you're not aware, is sort of a generalization of abelian. So what it means is that if we iteratively take commutators of commutators, so if you look at this first step, this is the commutator, and then we take the commutator of that with G, then we take the commutator of that again with G. This series eventually terminates, meaning that eventually we get something that looks like the identity. Of course, for an abelian group, it terminates immediately because the commutator of G looks like the identity in that case. So it's sort of a generalization of abelianism. So you can see immediately that this is a very algebraic fact about a group, right? It's sort of about it being abelian. It's not really something we could learn from looking at a Cayley graph, for example. I don't know how you would show that it's virtually nilpotent, but the way that we understand this is from a really geometric point of view, from looking at the growth rate of this group, and in fact, the polynomial growth rate. The proof of this is very non-trivial. It's a very difficult proof that's been revised many times over many years. You can find it online. Probably the best version is Terry Tao's version, which is relatively recent and is sort of the most elementary proof that's yet been given. And because of this characterization, because this is an if and only if statement, that just means that virtual nilpotence is another quasi-isometry invariant, which is crazy because quasi-isometry is a really geometric thing, and we get this algebraic invariant. That's awesome. Okay, and the other thing I'll just very briefly touch on, and I'd love if you asked about this, is a formulation of an important theorem called the Schwarz-Milnor lemma for growth of Riemannian manifolds. This formulation is due to Clara Löh and her book Geometric Group Theory. And pretty much the statement is, if we have a closed Riemannian manifold M with universal cover squiggly M, then the Riemannian growth of the universal cover is quasi-equivalent to the growth function of the fundamental group of M. So we define growth a little bit differently here, but you can see it's the same idea. Now, since we're in a Riemannian manifold, or rather the universal cover of a Riemannian manifold, we can actually just look at volume. And of course, I can elaborate on this more if you have any questions about this. But the growth of volume of balls in the universal cover is quasi-equivalent to the growth of the fundamental group. Again, this is a very non-obvious thing. This is very non-trivial. And it's sort of a broader application of another theorem called the Schwarz-Milnor lemma about quasi-isometries. But basically the reason for this, which again I'd love to elaborate on if there are questions, is that the fundamental group of a Riemannian manifold acts very nicely on the universal cover via Deck transformations, which are in some sense geometric. So anyway, thanks so much for listening. This is a subject I find really interesting, and I'm glad that I can share some of it with you. If you have any questions, please let me know. I'd love to answer them and think about them and talk about it more. But in any case, thank you so much.